So I'm just going to talk for a little while about agent-based modeling. Click to add subtitle. What is agent-based modeling? Well, the easiest way to describe it is probably to build one. So I'm going to go through building a very simple model. It's kind of the Hello World model that kind of everyone builds as the first model, which is the predator-prey model. I'll go through that in a minute. It's a modeling technique, obviously, and there's kind of three things which you have to remember about it. 3 points. First, models are made up of agents, and all these agents are small individual units that interact with each other. And the collection of all these different agents in an agent-based model is called a system. And the interaction of all these agents doing different things and reacting to each other causes emergent behaviour to happen in the system. So you get all these different types of agents talking to each other and doing different things depending on the rules that you give them, and this is what's happening at like the macro level, on the micro level, sorry, and then on the macro level you should see really odd effects depending on what happens at the micro level. It's kind of hard to explain, so we'll go through building one. So the key thing about agent-based models are you have simple agent rules at the micro level, but very complex things happening at the macro level. Not so much in the model I'm going to show you because it's kind of a Hello World model. So let's start by building a very simple, what's called a predator-prey model. So the first thing any agent-based model needs is an environment. So here my environment is a field. We have grass in the field and mud in the field, and that's it. So then we add some agents. So it's a predator-prey model, so we're going to add some prey agents and some predator agents. So that's two different kinds of agents in this model. All the prey agents are represented by pictures of sheep, and all the predator agents are represented by pictures of wolves. And in this example I've just been randomly put into the environment, but it's up to you where you want to put them. Depends what you're modelling. They might be somewhere in the environment that has to be a set place, or it could be random. You can change it each time you run the model. It doesn't really matter. So then finally, before we run the model, you have to add rules to all the things that we've just created. So first we add rules to the environment, which is very simple. There's just 2 rules. First, that grass turns to mud if grass is eaten by an agent, and grass grows back after a certain amount of time. The second rule set is for predators. So all the predator agents have these rules. Then they are that they will chase prey. They need to eat prey for energy. So if a predator touches a prey agent, the prey agent will disappear from the system, and the predator agent will get what's called energy. If they don't have any energy, they'll die, so they'll disappear from the system. So they need to keep eating prey agents to stay alive. And predator agents can reproduce. So if 2 predator agents get together, there's a chance that they can reproduce, and what that chance is, the percentage or whatever, we can decide. We can set that in the code. So then we also need a rule set for prey agents. So prey agents have 4 rules, quite similar to predator agents, apart from they need grass for energy. If they run out of energy, they'll disappear. They can reproduce if near. Excuse me. And if there's no energy, if the agent has no energy, then they'll die. And so this is a very simple design of a predator-prey model, and this is what it looks like in a very popular agent-based modeling environment called NetLogo. And so what happens is you design this model by writing code. It's very, very easy to write in NetLogo. There's lots of examples. Logo is based on the language Logo, so which in turn was designed to teach children how to program. So it's very easy language to pick up. I think what's difficult about it is it uses Logo terminology, so it calls agents turtles and the environment a patch, which is fine if you've done Logo and you know that terminology, but it can be a bit confusing if you're new to agent-based modeling and you're new to Logo. But still, it's a great piece of kit. And here is our environment that we designed, and here they're all the integers and variables that we design in the rules. So, for example, there's a slider here which lets you change the plant regrowth rate. I'll get onto what these buttons do later, but you can change how likely it is to reproduce. You know, how likely different agents are. So you might want to run a model where the prey will reproduce faster than the predators, or vice versa. And down here, it's very easy to create graphs of aggregates of values. So this is population. So I think the red is predators, population of predators, and the green is population of prey, and this is an aggregate of the average energy values. So in this scenario, they don't have a lot of energy, so we might need to find a way of pumping energy into the environment. So what happens is you build this, you click go, maybe this will work. Yeah, so is this going to work? Yeah, so you build your environment, you click go, and then all your agents move about compared in accordance to the rules that you wrote. So here we saw a big explosion down here of prey because there was lots of predators. Sorry, because there was lots of predators in one area. But then they ate all the all the prey in that area and ended up dying out. And up here we saw that we ran out of energy because they ate all the grass. So then they had to disperse. And so it was just an example of what might happen in that environment. So I'll get on to why I've shown you this example in a minute, but first we'll it's just kind of worth thinking about what we did there. First we created a world, and then we watched how that world developed for interactions. And so the world events of the explosion, dying out of predators, or the world event of running out of grass in a certain area of the environment, they all happen because of the interactions of the agents. And so you can then go back and edit the world and run it again. So what happens if you find a way of making grass grow faster? I don't know. Well, let's put the slider higher. Does that mean that sheep have more energy? They reproduce. They stay alive longer to reproduce. There's more of them, which means the prey don't run out. The predators don't die out because they've got more things they can eat. I don't know. You can try all these things, and that's what's great about agent-based modeling. You can try different setups by simply tweaking the rules. Very, very small tweaks could end up in something completely different happening. The reason I showed you this particular model, this is a model that someone else has already written, and you can download it from a place called Modeling Commons. And the reason I showed you this one, this is a description of the model here, and this bit of highlighted in red is important because this model actually lets other users dial in to the model and take control of one of the agents. And so you can actually put yourself in the model. So what happens if I'm a prey and I decide to hide in the corner? Or what happens if I'm prey and I decide to reproduce as much as possible? Or what happens if I'm a predator and I don't know. You get the idea though, that you can participate in the model, explore different things, and then you can also go back after you've explored what you can do in the model and go back to the creator of the model and said, I tried doing this when I was participating in the model, can you add this to the rule set? So it's kind of like a game-like environment to explore what the creator of the model wants you to explore. And in this instance, it's exploring population dynamics. So someone's gone away, taken some equations for population dynamics that I don't know much about, but they've taken them and they've created a NetLogo model, and then they've let students come and play in that model. So the students are learning about these equations. So sorry. Yeah. So not all models are physical things. They're not all fields and prey and predators. There are some other models that I've played with which are completely different. One model I've played. These are some that might be interesting to a project that I'm working on at the moment. The skim model is a model which tries to. It's created by some researchers in a university in Surrey that tries to mimic how knowledge is transferred in networks. And in this model, agents aren't individual people. They are things like firms and universities and consumers and suppliers. I spelled innovative wrong there. I spelled it so wrong that it can't even correct it. I'll have to remember to change that. So it doesn't have to be a single thing. That an agent can be scaled up. So an agent in a model could be a university. It doesn't have to be one person. This model I thought was okay, but I didn't think it really simulated. It wasn't what I saw actually happening in the real world. So for this model, I think the advantage of it was it helped me understand what the people at Surrey were thinking about how knowledge is transferred, and I disagreed with it. And I thought it was good that it gave me a way into their head, even though I don't think you could predict the future of knowledge dynamics from that model. There's a lot going on in supply chain modelling and consumer decision making, and there's different ways of building a model. So the model the model which we just saw was built on some equations for predator-prey dynamics, but the consumer decision model that you can download from this website, I've not tried it yet, but it's based on the responses of questionnaires. Somebody went out, they did a questionnaire, and then they built the rule set for the model based on what people had, what results people had given for that questionnaire. So just to recap, the key kind of points are you can see these big things happen on the macro level, like populations dying out or populations exploding, based on small things happening at the macro level, on the micro level, on the level of the agents. And so through the interactions of these agents, we see big things happening based on very simple rules. Also, I'm going to change the title of this. No, I'll keep it like it was. I think it is key points, isn't it? It's flexible, so if you don't like your model, you've run it once, you've seen some interactions which you don't think are right, and then you can just change it before your next run, or you can let someone into your model, like that model we just saw, and they can give you feedback and you can instantly change it. So this is kind of a iterative, agile approach of just carry on, tweaking, trying again, tweaking, trying again, and I think your mind's always in the zone of where am I going next, and you're always learning about the environment that you're modelling, and so I think that's a great thing about agent-based modelling. And also there's lots of software available. Again, I can't spell. So this is my personal opinion now about agent-based modelling. Some people are really down on it. They don't really like it because they think it's very, very hard. Because you're modelling individual agents and how they interact with each other, they say it's very, very hard to model all the things that those agents could do if they interact. So like, we had very simple agents that a predator would always kill its prey, but that might not be the case. There could be lots of things that stop it killing its prey. And so some people say you can't predict the outcome of a system very well for agent-based modelling. You're best off having a top-down approach rather than a bottom-up approach. I don't think that's true. I think it depends what you're trying to model. Sometimes it is very difficult to predict exactly what's going to happen. But saying that, it's a great way to explore what might happen. But there are cases when you can predict what's going to happen. So, like in computer science, you might have built, I don't know, a network in a lab, and there's computer science often has rules like yes, no, and there's a lot less that can happen. And in those kind of environments, you probably can predict what's going to happen. So I think it depends on what the system is that you're modelling, to whether you can use it to predict what's going to happen or just explore what's going to happen, or maybe you can explain what's happening in that system at a small level. So yeah, I think it completely depends what you're trying to model. So finally, these are just some platforms. If you want to go away and build your own model, NetLogo is what I just used then. Very, very easy. It's based on the Logo language. I think it's brilliant. It doesn't scale up that well, so if you want to build massive systems, it might not be your. And if you want to have thousands and thousands of agents, it might not be your thing. There's a platform called Repast, which has two products. It has one that's a bit like NetLogo, but it's built in Java. So if you're a programmer, and NetLogo is annoying you a little bit because NetLogo is so easy. You put all your code into one file, but then when you try to build a big system, you're kind of wishing that you could, build classes, and you wish you could do your agents properly through polymorphism or whatever. That's what you might want to do Repast if you're a bit more of a programmer. The second system that Repast is one based on C++, which is kind of really hardcore, but it's built to be put on supercomputers or clusters or whatever. And so if you want to simulate thousands and thousands of different types of agents, perhaps, and you want to scale that up so that there's thousands of interactions happening every second. That won't happen in NetLogo, but you can do that in Repast. And there's another one called Swarm, which I've not used. But that seems to be quite popular. So these are some sites you might want to check out. NetLogo is what I used. Jazz is the biggest journal for agent-based modelling. It's got a social simulation spill to it. And Modelling Commons is where I got that model that I just shown you from. And that's it.